Thanks for the very kind introduction. I'm very excited to be here today and talk a bit about what we're looking at in terms of how to understand the 3D world and potentially how to interact with these environments. So what we're looking at in my lab is capturing the world from commodity kind of sensors. You have a 3D environment like the one around us. We want to take a cell phone camera or some kind of easy to access kind of device, take an image or a video and be able to understand what's going on in this environment. So the geometric structures, how we can potentially create an interactable environment you can, put into a video game level or something like this. So of course, there's application here in terms of content creation. So creating these kinds of virtual assets that can be interacted with in terms of virtual real kind of interactions. And also for, like I mentioned, video game or other kind of content creation scenarios, it would be cool to generate these kinds of environments such that you have a lot of flexibility in terms of how characters can actually move around and interact with these environments to make them seem more real and immersive. Of course, you guys here are all from robotics and the GRASP lab. I think there's a strong tie from how to allow machines to perceive the world in terms of similar to human perception. So hopefully that also tells us a little bit about how we can then use that for robotic interaction, perception. And maybe you can tell me also a little bit more about this side because I'm working more on the perception side. But, the goal being robots that can actually act, in a way similar that humans can in these kinds of environments. So during my PhD, I worked a lot on how to potentially reconstruct these environments. So this is a bundle adjustment formulation for RGB-D frames that can do real-time reconstruction. And that enabled us to collect a lot of scenes at scale. That's the ScanNet data set that we collected, about 1,500 scans of this kind of RGB-D sensor quality sort of Connect style kind of cameras that enable us to go ahead and start to drive data-driven approaches in 3D that are having the capability of understanding some basic notions of semantics, object classes, object instances in the 3D space. I wanted to mention briefly, I'm interested quite a bit in both the generation, but I want to talk mostly about semantics today. But in case you're also interested in terms of more of the reconstruction-oriented setting, that's also something that we're very interested in. So the 3D perception task, I think, is pretty interesting because we as people are extremely good at it in some ways, which is that if you look at this particular kind of image, you pretty much get a good sense of the shape and structure of all of the objects and their layout in the scene environment. And it's a highly underdetermined problem because all you have here are the RGB values, so we can see the backside of most of these kinds of objects. So actually generating the 3D structure of the scene behind it is a challenge and in a sense has a lot of ambiguity. So we as people have a very good model of understanding, what are likely possible reconstructions for this kind of environment, what are common sizes for things like stools and couches and so on that resolve things like, depth scale, ambiguity from binocular perception. And that means we also would like to rely on having a strong 3D prior when we want to give machines this kind of perception. So this is, I think, also related to this model-based recognition paradigm in more early robotics, where you want to be able to recognize objects by saying, okay, we have some kind of template understanding of what we would like to see and perceive. And so the matching problem of matching that to a given set of templates is a lot easier than the more generative formulation of reconstructing a whole 3D scene environment. So that's something like saying we have a database of 3D shapes. Can we represent the objects in the scene by retrieving and aligning similar structured models to represent these objects in the environment? And this is also useful in the sense that these databases 3D shapes are typically constructed by people such that they are they fit immediately with downstream kind of tasks like rendering and so on in a very efficient, very compact kind of fashion. And so that means that if you use this for some representation, you get out a really nice representation that fits exactly with modern graphics kind of pipelines. So you can do something very simple here, which is to say that, okay, from an image, 2D models are pretty good at recognizing objects in 2D. So if we just take the detection and segmentation from the image, and we know what the corresponding 3D shape should be, we can learn an embedding space and try to enforce such that the image features corresponding to objects lie close to the 3D features corresponding to the shapes. And the ones that are far away should be pretty far away. This is basically deep metric learning in order to construct this kind of space. So then at test time, when you take an input image and a detected region of it, you can just query into the space and find the nearest neighbor, get the object that represents that particular image, and simultaneously estimate the pose. So this is the shape of this kind of embedding space that's been constructed here with a contrastive loss formulation. And you see that you get this nice kind of separation in the sense of different kind of structures, despite the fact that they come from different domains. So you have these browse tables here, bookshelves down here, and they are still clustered a little bit by domain. Obviously, the feature sources are still a bit differently structured, but you end up with very similar structured objects.
Did you say you have paired CAD objects for each detection in the data set?
Right. So this is relying on having this information available for training, which is, as you might imagine, it's a fairly restrictive constraint because it's not that we have tons of these data sets. However, we did work on constructing such a data set that has the CAD models available. There is a bit of a caveat that this particular setting, there's not too many data sets. So there's this Pix3D data set that we're showing here, which has these nice kind of clean, almost IKEA style kind of images or objects. And the database of objects very nicely actually corresponds extremely well. So that means that you can get these really good reconstructions that have been structures or like that go past exclusions in these kinds of regions. Granted, this is a bit unrealistic because the setting is that you actually do have effectively the ground truth shape available. And in practice, that's not a very realistic assumption to make. You might have databases like ShapeNet or Optiverse, but the chance of them actually matching precisely in terms of geometry is pretty low. So if you make this a bit more robust by doing, instead of at an object level reasoning, you can do this at a patch level reasoning. So try to find similar patches between objects and have them vote for what the best representing object should be. And that means that you can do this patch-based reasoning and get objects that are at least much more structurally similar to the kind of input chairs that you see here, and definitely way better than this object-based reasoning here, where you have all kinds of different objects being retrieved in terms of the shape. And this is precisely just the challenge of that there is no exact CAD model that matches this particular object in the data set. So you need to be a bit more robust in this kind of reasoning. And this patch-based reasoning also means that you get a much better structured space when you query the top n nearest neighbor rather than the top one nearest neighbor. So here you have this input image with the detected object. You can see the ground truth shape here just for the purpose of visualization. And if you do it patch-based, you end up with a bunch of couches that look kind of similar, at least in terms of the structure, whereas this one falls off immediately from the top one to start producing like L-shaped couches and so on, because it's very much overfit to the shape-to-shape similarity. That means that space is not so well structured and less generalized. Well, and the same goes for this particular chair. So this one doesn't even match all that well on the top one and produces kind of, desks that don't quite look exactly in the same kind of structure. Whereas here you can see also, there's not exactly a ground truth that exactly matches. But they all share much more similar parts of the characteristics. On the other hand, like I mentioned before, it's not enough to fully capture this reconstruction setting where we want to understand the objects, because inherently, there's just a lot of ambiguities in this kind of reconstruction setting. So from monocular perception, you have this ambiguity of depth and scale. You have also partial observations of objects. In fact, it would be much better to build a probabilistic approach to reconstructing the scene here. Because in a sense, when we look at this, we have a general understanding of what the relative shape structure might be, but we don't know exactly how large that particular couch is. We don't even see the end of it actually even in this image. And so we want to be able to understand this and model these different kinds of possibilities. In fact, the other limitation that you've also mentioned is that if we have a better probabilistic model, we might be able to train only on synthetic data where you have this notion of being able to generate an arbitrary number of paired image and CAD data and still be able to transfer to rails. So what we have here is an approach that generates a multi-hypothesis reconstruction of the scene. So we can sample n hypotheses. You see these 3 different hypotheses of the reconstruction of the scene. In particular, the size of the couch is varying here because we don't know exactly how large this particular couch is. And if we compose them all together, which hopefully is coming, you can see there's also a bit of this notion of modeling of depth scale ambiguity. So the camera is on the top left here. And the scene, it's possible to explain this kind of image by either being closer and smaller or larger and farther away. And that is also being modeled in this distribution that's produced by this method. So what we're doing here is...
Would the depth estimation help with that is the case to alleviate the uncertainty?
We are relying very heavily on depth estimation, but it doesn't reduce the ambiguity in the scenario. So monocular perception is inherently depth scale ambiguous, right? So that depth maps, especially depth estimators, are extremely good at relative depth estimation because you don't know actually it's exactly 1.5 meters away, or maybe it's actually 1.7 meters away and everything is just a little bit larger. So that ambiguity still exists. So we need to resolve the depth scale ambiguity and this notion of partial objects and inexact matches in terms of the CAD-based description. So what actually mainly allows us to train on synthetic data is that we rely very, very heavily on depth estimation, and depth is much more, the domain gap between synthetic depth and real depth is much smaller than the domain gap between synthetic RGB, which looks very, very synthetic, as you might be able to see in this kind of image. It doesn't, I mean, at first glance, it might look kind of realistic, but this looks too clean and perfect to be a real image. So we have a machine generated depth estimate, and we're trying to model the probabilistic distribution here first of scale. So scale is one of the big uncertainty sources in terms of monocular perception here. So this is a diffusion model, since diffusion will allow us to capture a probabilistic model of a bunch of data sources that literally just models the same scale here. So here we have a diffusion model that's taking as input the generated depth estimate and outputting the difference in scale of the actual scale to the scale that this depth estimate is actually providing. So we're trying to estimate the scale that should be applied to the particular depth estimate in order to shift it to the actual scale. And so this is allowing us to sample multiple different types of potential scale explanations for the depth estimate. So here you can see a couple of different samples. You end up with the same kind of thing. If it's smaller, it's a bit closer to the camera. If it's larger, it's a bit further away in terms of distribution. So once we model the scale, then we can try to model the pose of the object. So here you have as input basically the machine-generated depth estimate and machine-generated object mask that gives us an estimate of this partial point cloud. And that's what's taken as input into this diffusion model that actually models the normalized object coordinates of the particular object. So on a per point basis, you're estimating its coordinate in the canonical orientation of that actual object. So this is actually much more robust than directly trying to output, like 3 degrees of rotation and 3 degrees of translation. Because it's a very dense, overdetermined descriptor, and we can still solve for the rigid transform of the object from the correspondences given between the and the normalized object.
Does it also handle, because of the way that you said, for each point you output now a new coordinate, you can also potentially do not just rigid rotations and translations, but maybe also things like stretching of the object, like affine transformation.
Yeah, so you can potentially solve for anisotropic scale. I think if you want to do a little bit more, it's possible, but it might be more challenging to represent the actual deformation grid. Here we're just solving actually for the 3 degrees of rotation, 3 degrees of translation, 3 degrees for spin. So we don't have more complex transformations in terms of shearing or something like this.
I guess it doesn't matter because you do happen to, in the setting, know the CAD models fully.
Yeah, so we do want to be able to stretch the objects a little bit. So there's 3 scale parameters, but other than that, we don't have any other transforms available. All right, so this will model different potential object poses. And then finally, we have the object shape that's also being modeled here. And this is also important for being able to generalize to scenarios where we don't necessarily have the exact matches, is to try to include these objects into a feature space. This is pre-trained in terms of feature encoding of the objects. And then we take in the normalized object coordinate estimates for the object in order to then predict the object weighting that corresponds to that particular object. This is again being modeled as a diffusion process so that we can sample probabilistically for different explanations of which objects potentially are matching to the image. So this is pretty much a cascaded process where we can then go from scale to pose to shape. And then all that we have to do here is do nearest neighbor retrieval into the database of shape encodings for the actual shape. So at inference time, what happens is we get an RGB image. This is actually now a real image, so you can see a lot more of the complexity of the real, especially in terms of lighting. But this we can sort of mask away in the sense of this is a machine-generated depth estimate. This is machine-generated semantic segmentations and instance segmentations. So we first try to estimate scale. So that's taking in the depth estimate and producing a couple of scale samples. And then based on these scale samples, we can scale the depth estimate and produce pose samples for the objects. And then here we can go ahead and take these sampled poses and directly try to find the corresponding shapes. So here we can now get a bunch of different hypotheses in terms of what kind of CAD models and alignments would represent that particular scale. So here you can see the 2 different hypotheses being generated by this particular approach. So this means that our method, and this is in comparison to CAD model and retrieval approaches that were trained actually directly on this data set that we're testing on. So ours is trained only on synthetic data and applied to these real images. And we can actually get more robust retrieval and alignment. So here you can see the scene from a couple of different views for these objects. When you have things that, for instance, this table should be, you would think, a little bit easier because you see most of it, but actually most tables in the database are square. So that's why they typically retrieve square-based tables. And you actually don't completely see the legs of this table. So it becomes a little bit challenging to get the orientation exactly correct here. And the couch, you have the same thing as before. It's a little out of the image. So that makes it more challenging to get the correct alignment and retrieval for that particular example. So this is really nice in terms of having this really strong synthetic spreader. It works particularly well on common occurrences, right? We are training on synthetic data, which means that it's going to be difficult to capture objects that aren't in the synthetic data set. So that means we mostly can do things like chairs, tables, bed, big furniture kind of objects. But real scenes in practice, they typically do have much more complexity and diversity in terms of the composition. We're not just making scenes with only chairs and tables and beds, right? But this means that we need actually data that can actually capture this level of be in the environments. So previously we were working on the old ScanNet data set that I mentioned we collected with a bunch of commodity RGB-D kind of sensors. But the quality is mediocre at best in terms of the reconstruction. And that actually means that the semantics suffers because you can't recognize so easily these objects because they're very noisy and partial. And you see the annotations are a bit tough in some of these regions where like the whiteboard blends a little bit into school. So what we've done is we've gone to the other extreme and worked to create a very high fidelity capture setting for geometry so that you can actually get all of these small fine scale objects captured in the geometry of the actual scene setting. And that means that we can much more easily segment them in terms of the semantics. So these are both annotations that have been annotated by people. And one of the big challenges in this kind of setting is that it was hard for people to recognize a lot of the objects actually in the environment because the geometry is a little bit messy there. And this makes it much more clean. In fact, that translates to not only these kind of small objects that you see on the desk, but we're also capturing much higher fidelity appearance. And this is a DSLR camera in the capture setting. So this is much better than this is a very old iPad RGB color camera from a video stream. So this capture setting is high-end in terms of geometry, in terms of DSLR color appearance, but we also do have the iPhone capture to represent what is the more commodity sensor stream from capturing this kind of setting. So iPhone RGB has improved considerably since a few years ago that they've had these kinds of cameras, and it also has a depth stream, which we capture as well, so that you have the alignment between commodity sensor color and geometry, as well as the high-end sort of pseudo-geometry capture from these high-fidelity sensors. So in practice, this is a far laser scanner that captures the geometry. Is about 1 millimeter resolution. And each sweep of this scanner takes about 40 million points. To capture a whole scene, you would place that camera, the scanner on a tripod and move it into multiple locations in a scene. So this is a pretty expensive process in terms of the capture. It's not nearly so portable as taking an iPhone and scanning the stuff around. But that is hopefully what you would be able to do with this kind of sensor data to map to create reconstructions that match more with the high-end outputs. So the DSLR is the Sony Alpha 7 and the iPhone 15 Pro for the RGB stream. So in the end, you can get these nice reconstructions with much more fine-grained semantics, especially all these kind of small objects. You can finally start to get the ground truth annotations as well. And then here you can see some of the instances. I think it's nice you can get all of these individual plates just due to the geometry capture here. So because we have good appearance capture, especially with the DSLR, you can also do novel resynthesis. Video that should go back and play. So this is an example from one of the scenes of from your facto, just the neural optimization and putting a virtual camera through the optimized scene. So this also means that we get pretty high quality view synthesis from DSLR images that can be used for more appearance settings. So we've released this data set as ScanNet++. What you see here is the release numbers. So there were 380 scenes, not a ton, but we are currently still expanding this data set. And so what you see here on the right-hand side in parentheses is the number that we currently have in terms of the collections up until now. So we're hoping to release a second version of this data set that's much larger scale, about 1,000 scenes in a few months, so that people can start to learn more general priors, which might be a little bit tough on a smaller scale. And these are all the test scenes that are already released. So in practice, it's a bit closer to 300 scenes. Because a bunch of these are test scenes as well. And that, I think, will allow for a considerable amount of generalized that can be learned on high fidelity geometry and color. So I think this will hopefully provide a little bit of a stepping stone for more realistic environments that have tons and tons of, this kind of clutter, small objects. How can we actually start to represent real scene environments? But they're all static, right? And real world scenes are in fact dynamic. In fact, most of the time they are actually dynamic. If there's a way to capture very large scale, and by large scale, I mean more on the order of thousands, not like on the order of millions, diverse 4D data, I would like to know, but I don't have the solution to that to capture something, of the thousands of dynamic scenes that actually have the sufficient diversity and complexity in terms of the objects and the motions that occur there. So what we can do is maybe focus on a more constrained setting, which is to say, okay, maybe not a whole scene, but just a single object. Can we learn how people interact with these objects, given the object and brief text description, right? So here the object geometry is given. It might look a little bit imperfect because this is a scan of a real object, not a synthetic picture. And we want to be able to produce, possible human interactions with that particular kind of object. So this is outputting a simple model representation of the person and also the rigid transform of the object as we move through time here. So the thing here, of course, is that from a very naive perspective, one of the most critical aspects of this interaction is just the contact. So if you visualize the contact as a heat map over the person, this is red is closer, blue is further away, then you see that this actually fairly well describes this kind of simple interaction in a sense. It's mostly characterized by the part of the body that's closest to the particular object, and that's driving the interaction. So if we explicitly guide and model contact, and here you see for just a couple of other examples that this is very strongly correlated with this simple kind of contact map being computed on the person, then we should also be able to get more accurate models of the actual dynamic. And these are just grounded contact. It's not something that we've done here.
When you say contact maps here, you're not ever kind of thresholding and discretely calling something a contact or not a contact. You're just kind of providing a distance to
right,
contact.
It's just a distance. Yeah. And the distance over just uniformly sampled points on the human body. So just here.
Yeah, but you would imagine that actually contact in particular is one of those things that is either there or not there. Like it's not so much as important whether it's 1 centimeter away or 10 centimeters away. It's more important whether it's in contact or not.
There's a level of truncation at which contact, like if it's at so far away already versus twice as far away, it doesn't matter at all. But close to the surface of the object, then you do care whether it's maybe 1 centimeter away or 2 centimeters away, because that's telling you a lot more about how the potential interaction might occur. Right. So I think you're saying, yeah, we could probably threshold it and truncate it at some point. Certainly, that I think would be useful to allow the model to focus more on near surface kind of things.
Yeah, I guess, if it is the case that literally truncating what you already have right now will indeed give you true contacts versus non-contacts, then it's a non-issue. But I guess the question is whether the resolution of what you have right now is sufficient to capture that qualitative difference between two objects are actually currently in contact versus they're not in contact.
So that's for the data we're working with, which is captured from real scans. It's never quite exactly binary.
Gotcha.
Because it's just a little bit too much noise in terms of the actual capture setting itself.
Yeah.
But it's probably something where you would have the ability to interpret it. I think truncating is not 100% correct because it is a human body, and that's certain pieces are usually tied with each other at a high level in terms of structural movement, especially when you think of just stuff like walking. So you can carry a backpack around, so that contact with respect to the backpack is important, but the walking motion is also important. So I don't think we can completely ignore the rest of the stuff, but certainly I think if you take a more local view on contact, that might. Right, so we want to just model the human object and contact all together. So here again, we have just the input, which is the geometry of the object. This is interpreted as points. and the text description. So these are being used as condition for a joint diffusion process over the person. This is a sequence of symbol body terms. This is the object, and this is just rigid movement only, so we don't do any deformation of the object. This is rotation and translation over time. And then also we use this, you can almost imagine it's almost redundant because this is information that's computed from both the human and the object. But it helps to explicitly parameterize this contact as this heat map of distances over the person. And here, in terms of training, this is joint training with a cross attention between standard modality. And you can see effectively the working process correct for the whole sequence over time. And we just want to output the same data modalities that allow us to produce the sequence. So the nice thing about explicitly characterizing this in the model is that we can then use this information at test time to help fix out some of the synthesized dynamic sequences, because there's no hard guarantee here that you will actually end up with a contact that actually is the contact that represents this person and object. And so it is the case usually that the contact that's being sampled out of this diffusion model is not quite same as the contact that you would compute from the person and the object. And you can actually use that information to produce a better output synthesized sequence, right? So first you would just sample from the diffusion model in terms of the object. But the idea behind it was that you can use the difference between the actual contact between your sampled human and object, compare it with the contact map that is being predicted, and then update the model so that you end up with a correct contact between human and object. And that actually avoids a lot of these issues with the object kind of floating a little bit away from the person as they move around. And so here, hopefully you can see example video of a synthesized interaction. So the input being carry a suitcase and this object suitcase. And here the person around with the suitcase. You will notice that it's not exactly the correct grabbing motion because we don't actually, we use a simple version of simple and we don't model the difference in hand poses here. So the hand is always stuck in some kind of default resting mode, which is why it might look a little bit funny here in terms of the suitcase. But I think we get
to calculate this the kind of the distance map, something like that.
So
it's
during
just
training,
the distance between the
it's
object
literally
and the
just the closest distance from the object to the human, wherever the point is on the human. So you sample a bunch of points. We had 128 points sampled on the human, and then just compute the distance from the closest distance of these points to the object geometry.
I see.
And here's another example of move the chair backwards. In fact, what happens here is the person moves it backwards and then it's the object. So, I think this is also because in the data, there are very few human chair interactions that don't have the person sitting on the chair. So they'll move it back in order to just perform the sitting action. And here we have a comparison with some of the, oh, it didn't play. Well, we can stick with this one. So this is this interactive model that's modeling human interactions. And you see there's like often these floating object kind of occurrences, whereas the contact guidance here actually means the object typically follows the human quite well. So this is also reflected in terms of a user study, which unfortunately, it's kind of the most reliable way to evaluate these kinds of results because we don't have very good perceptual metrics from a quantitative perspective that tells us how good these synthesized sequences actually are. But people find that this produces more realistic sequences that better follow the text prompts. In fact, you can also see that if we don't model any contact training process, you end up a lot with these similar kind of floating artifacts that you saw in the previous state of the art. If you model contact but don't use it at test time. The object follows the person well, but is usually a little bit shifted. And then finally, if we model the contact and then also use it as some guidance in the synthesis, then we can get a much better interaction with the object.
Another question about the contact, but have you ever try also imposing a contact on the object? So, because maybe there's some cases where you do, but I mean, there's a specific place where you have to put the object, so that's also important, right?
Mm-hmm. Yeah, so we haven't actually tried it out. I think it would be useful. There's a little bit of the same goes for the person, by the way. There's a little bit of an ambiguity sometimes, which is that sometimes the person gets close to the object as they're, trying to grab it. So you get the contact of them grabbing the object, but also the contact of the other body parts, legs and stuff like this that are usually around the object, that have a bit less to do with it. But maybe if you have also a better, smart, thresholding of what contact might mean in that kind of scenario, but it's more often that you end up with the legs of the person quite close to the object, and that disrupts a little bit of the naive version of contact that we use here. But I think it would certainly be useful to know where from a functional perspective, where the people usually do grab objects, right?
I'm just saying the inverse, right? For every point on the object, you define the closest. Right.
So here on the object, you would have quite a close contact, despite the fact that that's not the major sort of source of motion. So I think you need to learn at something a little bit more sophisticated than a naive distance map. But I'm from the perspective of just functionally knowing, okay, well, this person is going to grab it from the top or the bottom. That's definitely going to be useful.
Maybe a quick follow-up question, but this term contact map, did you coin it, or is it from some paper? So this feels, it feels like this is a more general contact. It's not just contact, but it's relational proximity. So it's much richer information than actual contact.
Right. Contact, generally speaking, has been used a lot in terms of modeling interactions because very natural kind of thing to think about. The specific form of contact-based sort of distances are also used. The specific form of this kind of contact heat map, I think there are some concurrent works that also look at this and also from hand-object interactions, but they're not from the body, human body-object interactions. But yeah, it's a very sort of natural idea to try to figure out how to better model contact to model the actual interaction.
That'd be right to note that maybe your visualizations here also don't really have too many instances of the human mesh and the human shape and the object space kind of intersecting and kind of going into each other. Whereas I think in some of the earlier visualizations you showed of prior work, there was a little bit more of that happening. Are you doing something to specifically model that, or?
So this is only modeled implicitly. Okay. We don't have an explicit penetration response. In fact, actually, independent of how realistic these actually are, I think from just a human perspective, perceptual system, we notice when objects float a lot more than we notice when the human hand penetrates the object slightly, as long as it's not super dramatic. So just the diffusion process modeling through data allows for this implicit understanding that there's not penetration, but it's not the case that we don't have any penetration. So we do usually have just a few vertices of the human body model slightly penetrating the object. But certainly you can probably explicitly import this as a loss as well.
Sure.
Is point modeling still exists in this process? For example, to calculate
the contact is actually represented as a point set, right? So it's point location sampled on the body, and then also the corresponding distances associated with these points.
So with the contact guidance, do you have a different sampling strategy? Because you already have the contact information, you can sample more densely around the contact.
That would be interesting. We don't currently model contact at a higher resolution, so it wouldn't help too much with this specific formulation of the model. But I think if you had one that allowed for a non-uniform representation of contact. And that would potentially allow for finer grained interactions that we're missing here, right? Like the hands especially. I mean, part of that is because we don't have a good tracking in the ground truth of the hands themselves. But I think what you mentioned would be really nice to model fine grain. All right. So here you can just see like a bunch of the different interactions. Sorry, this is a video encoding artifact, I think, because that's not actually even what we're capable of synthesizing, basically. All right, and here you get a bunch of nice different kinds of interactions, different chairs, objects, backpacks, and stuff like this. In fact, and I do think this is important because we're training on a fairly small scale kind of data set to see, what kind of new interactions can we potentially generate. So this is basically the generated interaction and the most similar one just based off of geometric distance in the train set. And you can see that the motion is being visualized in the alpha transparency of these particular sequences, that in fact, it can actually synthesize new sequences that are not the exact same motion as the train set. So this is a histogram of distances from the train set. So here we can synthesize sequences that are very close to train sequences and also ones that are much further away. So this is, I think, already nice, and it's mostly because the sequences are long, and so we can do a lot of augmentation by just looking at small chunks of sequences in the train set, despite the fact that there's about 300-400 sequences depending on the data sets that are being used here. But certainly, these data sets are limited in terms of number of objects and number of different types of objects. So for objects that don't appear in this data set, it's hard to synthesize a correct interaction because we've never seen the approximate type of interaction that should occur for these objects. On the other hand, you can do these fun things like given an object trajectory, can we actually synthesize, the human motion that corresponds with that particular trajectory. So this is just because it's a diffusion process, we can insert the object part of it and continue to use the rest of it. So here for this particular stool, it generates a person then putting down that particular stool. And you can even start to populate these 3D scenes and this is not doing anything sophisticated, we're just taking the chairs in the scenes and putting human interactions in here. So it's not necessarily aware of collision of other objects at the moment here. But we start to be a bit capable of understanding how a human might actually move around in an environment. Of course, the generality issue here means that in practice, we're not actually understanding the environment, we're just understanding individual objects. But that's very challenging with humans and scenes because there's very limited supervision data available. We typically are working with data sets that are quite nice, but they're very small scale. So we usually have 10, 20, 30 scenes in the same number of subjects, very limited types of interactions. I think, one potential source of interesting signal is to learn from video, because you do actually have a lot of 2D videos that tell us how humans are moving. It's just, we don't have the full 3D supervision here. We do, on the other hand, have data sets of, what 3D people look like independent of their environments. And so we can try to combine this together. The main thing is to try to overcome the lack of correspondence between the video and the 3D here. So what you can do there is just to say, okay, the actions should come from 2D, so the general semantics, and then also the 2D projections of the human body in terms of just skeleton joints. And then what we can do is then predict the 3D poses with a regularization term, basically saying that there's an adversarial loss, that the 3D pose actually is representative of a realistic 3D pose. So this is predicting the semantics as well as the 3D pose that's being regularized by general data sets of just 3D poses. And this means that we can actually do, I'm going to go through this. So just to see the more visual results, this is a forecasting task. So you have this input, a bunch of frames, and you try to predict what they're going to do in 3D. And so this is prediction here that can be performed with this joint modeling that takes in the 2D information of the general kind of actions that should be taken and 3D information. And so this is also challenging for other works to be able to handle this kind of long forecasting in terms of 3D understanding. So the thing is, of course, like, you see this, but it's not really an interaction with the 3D scene. It's just an estimate of a person. And that's the biggest challenge here is how do we really actually understand this setting under limited and imperfect data. The thing is, we do have actually remarkable advances in text and image understanding and in terms of the power of these kinds of models, right? In fact, you can even do better 3D understanding, like textualizing 3D with language. This is just one of the earlier works that we've done that allow for a better feature space, but I think actually other people have done this much better in terms of learning how to map text 3D together, even for more robotics and scene graph kind of planning applications. It's certainly not the end of the line here. But in fact, if we want to use this for interactions, maybe we can actually leverage something that's even more powerful here and tell us about the data that we're actually missing, right? So we're missing a lot of this information in terms of how people interact with environments, but image text models actually have a lot of this embedded inside, actually. So what we can do is query these models for their knowledge about, what sitting on a rickshaw might look like in order to synthesize the 3D version of the person actually performing that action. And so this we can do without actually ever training on any 3D interaction data at all, and just relying on the imaginative power of these vision language models. And so we have the input being a 3D scene with a location specified and a text description. And we want to be able to get these interaction priors from text image-based models that can do in-painting so that we can synthesize the 3D interaction here. And so here we can just take that location and render a bunch of images of the environment and ask the model, okay, can you in-paint me a person performing this particular action in these images? There's a little caveat here that the in-painting model will actually try to change the background, and so you won't end up with the correct output here. But we can take a look at the attention maps between the person part of the sentence in order to figure out where the in-painting actually should occur. And that produces a bunch of interaction hypotheses. Now, these are not going to be view consistent with each other. So we're just going to approximate them all with 2D poses and try to optimize for the most view consistent set of hypotheses here that allow for the 3D interactions. So here, there's a bunch of free variables that tell us which images to actually consider. And we end up with the ones that you see here as being taken into account to try to produce this particular. So I think this is quite nice because this means that we have the generality of text image-based model that can understand all kinds of different environments and produce a 3D view consistent version of the stuff, for unusual things that you don't never see in captured data. We can start to produce interactions, a person actually riding like a cow, or picking up the weights at a gym. And that starts to produce like a nice potential for how we can actually get these much more generalized understanding of interactions in 3D scenes. So in fact, there's a lot that we can do here, and it's not the fact that we want to be able to just throw away the 3D data entirely in terms of learning. You can actually understand quite a bit in terms of even just unsupervised learning from 3D data. And here we can perform actually a decent instance segmentation of the scene without any 3D labels at all. So I think, of course, in practice, what we want to do is not ignore entirely one mode of data, but actually try to figure out what's the best way to combine all of this kind of thing, right? So we have things like affordance priors that are very difficult to capture in 3D and 4D. But we get some kind of signal about them from text, images, and videos. And we want to be able to effectively bridge that with the data that we actually have available in 3D and 4D, because those are still strong sources, even if they're small scale of information. Like, I think it will be tough to get correct fine-grained contact modeling without having any kind of source of 3D or 4D data. And you do see that in the results that we generate as well. It's even less correct than the dynamic sequences. And so hopefully, also, I think people have been looking more in terms of modeling appearance, especially for robotics applications as well, because the appearance is an important way to bridge between image and 3D. So this is something that's still a very open kind of question, and hopefully we can then finally use these interactions to improve the actual 3D scene reconstructions themselves. So thanks for listening to the talk, and I'm also happy to answer any questions.
For the amazing talk. Any questions from? Yeah, go ahead.
I had a question about the contact category. So if I understood correctly, the contact field is actually just like the distance, like the sign distance field of the objects on point standalone view.
Right, there's no sign in this case, but effectively, yes.
Or actually, I guess it's part of my question. It's in order to prevent penetrations, like, is there any way to like embed constraints? The distance can be, I guess if it was a sign distance, you could say like it shouldn't be negative.
Right.
And I'm wondering if there's anything you have similar.
Yeah, so you can do that. And in fact, we did use this constraint for the human scene generation, because the priors there from the image and painting are so coarse that you need to add constraints about contact and penetration, so the person sits a little bit more correctly on the surface of the actual 3D scene. We haven't explicitly modeled that with the dynamic contact guided work, because we found that the proxy is strong enough to produce nice looking results already. But I think it definitely makes a lot of sense. I think the main thing then is some of these objects are, you need to figure out what the sign is. In this case, it would, I assume, mean the inside of the object and the inside of the person. So you should not be able to reach the inside of the object nor the inside of the person. For the person, I think that's pretty easy to compute. For the object, if it's a partial scan, like some of these ones are, you will have to approximate it in some way, because there won't be a watertight surface. But certainly it could help to avoid penetration, and then you can also use that test time to guide the diffusion sampling, even if you don't want to train it, basically.
One more question about the Jensen. So you showed like a static image and interaction, but is it easy, or what would you say are the steps to make a video?
Right. So obviously, we would like to be able to generate dynamic interactions. I think a very naive approach, and I think it would work. It's not the direction that we're exploring right now, is to just do this and keyframe it. There's a few minor logistical challenges with keyframing, which is that you will have to try to do a little bit of, at the very least, prompt engineering to make sure that your keyframes are actually the correct keyframes that you want them to be, because sometimes these models will try to just produce one kind of mode for an interaction and not necessarily the sort of start-end kind of mode of the interaction. So it probably works better for more commonly seen kind of interactions, where you have different kind of settings that they've seen in terms of, like, open a door, close a door. You've definitely seen an open door and a closed door. But in terms of, like, opening a mailbox, it's more challenging, because the model, like, already has an idea of what opening a mailbox looks like, and it's typically going to be either open or closed, and it's hard to encourage it to go from one to the other. But I think these are challenges that can be overcome, and then you can just keyframe it together and do a bit of the motion synthesis in between. I think that's quite reasonable. On the other hand, I think at this point, it would be better to incorporate like a true dynamic prior into the actual motion here. And that we're still looking into. So I'm not sure exactly what's the right way to get that dynamic prior. But at least there's a lot of potential sources for that information in terms of data and models that are available as well.
And now, yeah, I have a question. So I'm quite interested in using this kind of synthesized data for improving 3D reconstruction algorithms, but how far we're away from that? For example, I can see a lot of challenges here. For example, you mentioned appearance is an issue. I think also kind of the human currently lack of details, and also I think kind of how to synthesize the kind of realistic motions in this 4D things to help you to help with the 3D reconstruction algorithms, and also what kind of the distribution of your synthesized data, like how this well aligned with, for example, the data in the real world. So how do you see these challenges, and also how far that we can use this data for reconstruction?
Yeah, I mean, I think it's a big challenge. So some of that stuff is going to be, if you want to just say, I want to reconstruct a 3D scene that has all of these common sense interaction priors baked into them, right, in terms of being able to know exactly how the objects are moving all together, right, multiple human actors and so on. That's not going to be immediately solved next, right? But I think, let's say, one thing that's the big question there is basically how much physics do you need to model these kinds of understanding of reconstruction, because that is actually something that when we build indoor scenes, we have a very good understanding, or maybe I don't, but the architectural designer or whoever understands basically how the structures actually fit together such that they support all of the other objects, the other indoor structures properly. So you could actually go as far as to model that whole process. It might be enough to just start with, let's say, more of a common sense understanding of what these interactions would be. So in that sense, it's a bit like, can we get better than having these kinds of explicit penetration and contact constraints? Like, I think most works at the moment are modeling some notion of penetration and trying to model some notion of contact. But they're a little bit of fuzzy terms in a sense of what exactly it means, especially since sometimes most people think of contact as the functional contact rather than the distance version of contact, because you might actually get quite close to an object without necessarily interacting with it. And can we actually get a better model than just saying penetration is when you intersect the minus of the sign distance, and contact is when you're close to an object? I think that one is potentially achievable. And I think we want to then do the same thing, right? Like, so to say, okay, if you're going to have this chair be here next to the table, then the person can't sit in on it until they actually move the chair away. The same common sense goes to, well, okay, we cannot place the chair here and have it actually intersect with the table. That current 3D reconstruction methods are not constrained against these kinds of things unless it's by, again, these soft contact and penetration constraints. So that I think is going to be quite useful to model for more of a holistic understanding.
Yeah, thank you. Yeah, let's thank our speaker again.